In this video, I'll talk to you about predicting categorical outcomes. Categorical outcome variables are best predicted by a technique called logistic regression. I'll begin by talking a little bit about logistic regression, and then move into contrasting it with linear regression. We'll get a sense of the mechanics of estimation, and then talk about the goals of logistic regression, of prediction and inference. We'll cap it off with some exercises. Logistic regression, like linear regression, is a predictive modeling technique. It is similar to linear regression in a number of ways. The two ways in which it does differ is that the logistic regression can only take two values for the outcome variable. It also differs in terms of the estimation method utilized, but we'll focus mostly on the primary difference or first difference, which is that the outcome variable can only take two values. It is for this reason, because there are only two values possible for the outcome variable, that some people tend to call logistic regression as a classification problem, or it falls in the family of other classification models like discriminant analysis, trees, tree-based models, so on. One way to contrast linear regression to logistic regression is to think about it in the following way. In linear regression, the goal is how much is John going to spend? Thus, we really are concerned about shades of gray. Is John going to spend $2, $5, $20, $100? In logistic regression, the goal would be to predict, will John Doe buy? Thus, it's a binary outcome. John buys or he doesn't buy. It's black or white. Thus, one way to contrast these techniques, think about linear regression as being shades of gray, or predicting an outcome variable that's shades of gray, while logistic regression predicts an outcome that is black or white. The research questions you'd use logistic regression for include the following. How does one distinguish loyal customers for a grocery store from switchers? Identifying who is likely to respond to an email marketing offer. Identifying buyers and distinguishing them from non-buyers, or getting a sense of who will engage in a certain behavior. Specifically, which variables influence whether a person responds to a credit card offer or not? Is it that men under 24 with cats as pets are good prospects for credit card offers? So on. Let's understand the mechanics of estimation for logistic regression. Logistic regression model looks as follows. The right side of a logistic regression model, in short known as a Logit model, is very similar to that for linear regression. You'll note here that the right side consists of, in this case, only one predictor. We have here beta 0 plus beta 1x plus epsilon. This right side is identical to the right-hand side for linear regression. The difference is in the left side. The left side is a seemingly complex expression. The left side is the logit. Specifically, it is natural log of p divided by 1 minus p. Here, p is not the same as a p-value used in evaluating a t statistic or a z statistic. Rather, p is the probability of the outcome being 1. In other words, in a Logit model, the left-hand side of the equation models the probability that an event occurs. To break this down a little bit, you can think about the left side as being an odds ratio. More specifically, P is the probability of an event occurring. The event could involve somebody buying a product, clicking on an ad, responding to an email marketing offer, and so on. This is the event that typically the advertiser, marketer, or researcher is hoping for. occurring. 1 minus p is a probability the event doesn't occur. Then p divided by 1 minus p becomes an odds ratio. The probability an event occurs divided by the probability it doesn't occur. This odds ratio is then converted to a natural log. So natural log of p divided by 1 minus p is the left side. You might wonder, why go through the pain of creating this complex looking expression on the left? The reason can be explained many different ways. One way of thinking about it is it's purely for getting the job done. So if you think about the left side of a right side of a logistic regression model, if you put these numbers together, the numbers you're going to get can range from minus infinite to plus infinite. Unfortunately, your left side, what we are predicting is a categorical outcome, the occurrence of an event or non-occurrence. Therefore, the left side can only really take values 0 or 1. If you think about them on a probabilistic scale, they can take numbers from 0 to 1 with, all the numbers between 0 and 1. In other words, the left side is range bound, but right side ranges from minus infinite to plus infinite. In order to convert the left side to have the same range as the right side, we do some mathematical gymnastics. Natural log of p divided by 1 minus p has the desirable benefit of moving the scale from 0 to 1 to minus infinite to plus infinite. In other words, the values taken on by log of p divided by 1 minus p can range from minus infinite to plus infinite, just like the right-hand side. The equation kind of balances out nicely then. The method used to estimate the logistic regression model, or Logit model, is called maximum likelihood. This differs from what we've seen before for linear regression, which use OLS, ordinary least squares, for estimation. Here's the intuition I just pointed out to you, is that if you were to model merely probability, the numbers must be bound between 0 and 1. Natural log of p divided by 1 minus p moves the range to minus infinite to plus infinite. Let's put this in context and understand how this would play out in an example. Imagine a realtor is interested in identifying the factors that influence the sale of a house. Now let's define the outcome variable here as the sale of a house in 2 weeks. Therefore, P is a probability of sale in 2 weeks. Our outcome variable here is the probability of sale in 2 weeks. More specifically, if you would express this using a logit, it would look like the logit of p divided by 1 minus p equal to a linear combination of a linear weighted combination of the predictors, such as area of the house, number of rooms, age of the house, so on. Now, in practice, of course, we did this mathematical gymnastics of log of p divided by 1 minus p to get a nice range of minus infinite to plus infinite. But the ultimate goal of logistic regression is to figure out what the probability of the outcome variable is. To do this, one can rearrange the terms. When you rearrange these terms, you can derive from step 2, step 3. So what you have in step 3 is a very complex looking expression. The good thing for us is we don't actually do this by hand. The computer is going to give us that P, or probability value, to work with. Okay? But just know here that P is the probability of the house selling in 2 weeks, and we can estimate that by rearranging terms of this expression. Ultimately, our answer might be something like, you might get a P, or probability of the event, as being, let's say, 0.6. The last part is to convert that 0.6 into what our outcome variable is, formatted as. Our outcome is house sells or it doesn't sell. It's good to know that maybe there's a 60% chance the house sells, but if somebody desires a binary response, we need to translate the probability into a binary outcome. One typically might do this by setting a cutoff value. One might say, let's go with a cutoff value of 0.5. So any chance above 0.5 is categorized as a 1 and below 0.5 as a 0. And that would be the intuition behind saying if the probability is, let's say 0.6, we're going to say it's 1. Or you could set a different threshold as described here of, let's say 0.6. Either way, one has got to set a certain threshold like 0.6 or 0.5. Let's move along and visualize the logistic regression. So we get a sense of why use logistic regression. So if you look at data for logistic regression, it will look something like this. This is a scatter plot. It doesn't look much like a scatter plot, but it is exactly that. It might take some effort to convince one's mind to believe that this is a scatter plot, and part of the reason is because the points are not scattered all over the graph. They're scattered in 2 bands. The 2 bands indicate the 2 values that the outcome variable can take. Remember, the outcome variable can only take 2 values, 0 or 1. In this particular scatter plot, we're modeling gas mileage of a car being either low or high based on horsepower of the car. So the gas mileage can only be high or low, can only take 2 values, 0 or 1. So the points are in these 2 kind of bands. Now, the goal here is to figure out a line that goes through these points in such a way to minimize the distance from those points. If that were the goal, here's what one would look at with linear regression. That's your linear regression line that, as you can see, is not doing a very good job of going through all the points. Now, not doing such a good job is a relative statement. Let's see if we can find a better model to go through these different points. There are many other things you can consider, like some nonlinear type regression, like a spline. You can see the spline getting better. Another kind of spline here is getting even better, and a third model getting better. You can look at more kind of complex models like a GAM, a generalized additive model, which is the purple line here. And that's even better in terms of kind of fit than linear regression. Bottom line, linear regression fails in comparison to many other models for this kind of data. Lastly, we can look at here the red line. The red line represents a Logit function. The Logit function seems to do a pretty good job of fitting the data. So let's pit the logistic regression model against the linear regression model. Here you can see the Logit model is doing a much better job of going through the points than is the linear regression model. Because the shape of the Logit function is to be S-shaped, some people call it a sigmoid function also. But it's not hard to kind of see that a sigmoid or S-shaped function would do a far better job of fitting this type of data than would a straight line, which is what the linear regression is. Okay. Having understood or reviewed the intuition behind logistic regression, let's look at the twin goals of prediction and inference for Logit models. just like linear regression, logistic regression models have goals of prediction and inference. There are 3 aspects of prediction we're going to look at here. First, is the Logit model better than a baseline model? We typically want to see if our model is better than not having a model at all. We can do this by examining a statistical measure. Or we can look at even how well the model is classifying. The statistical measure is something called a model chi-squared. This is done by comparing the -2 log likelihood, some sort of an error metric, of the baseline model to that of the actual model we have. The next step would be to think about, if the model is indeed better than a baseline model, how good is the model? While there isn't a linear regression R-squared available, there are pseudo R-squares that approximate the behavior of the R-squared from linear regression. The ones we'll look at are Cox-Snell and Nagle-Clark R-squares. We'll evaluate them using our traditional heuristics of under 0.1 being weak, 0.1 to 0.5 being moderate, and so on. Lastly, we're interested in predicting how accurate are the predictions. This is similar to the concept of looking at an RMSE. We'll look at something called a hit ratio or accuracy to judge accuracy of predictions. The inference part includes three aspects too. First thing, which of the predictors influence the outcome? We'll do this by examining the statistical significance of coefficients. Next, we'll interpret the coefficients. This part is a bit, it takes a little bit of practice to get the hang of this interpretation part. We'll spend some time on that. Lastly, we'll examine the relative strength of the predictors to figure out which one is the most important. Okay, let's get to work. Let's look at an exercise here of credit cards. We're going to use a data set of credit card here. Our data set is right here. It includes, it's a very simple data set. We have an ID variable, offer, which refers to whether or not somebody accepted a credit card offer, their age in years, their income in thousands of dollars, their home value in thousands of dollars. Okay. Now, what we're going to first do here is utilize the age to predict whether somebody accepts a credit card offer or not. The possibilities for offer are 0 or 1. That's yes or no. Okay. So we're really keen on finding out what is the probability of somebody accepting the offer. What is the probability of the event? In this case, a yes. So I'll go here and say regression, binary logistic to get us going. And we'll move credit card offer over to dependent and age to covariates. You'll notice the terminology is a little different from that for linear regression. We refer to independent variables as covariates in logistic regression, at least in the SPSS menus. And that's it. We'll review the output now. Before that, let's take a look at our question. The question we are examining is, of course, whether somebody's age has a bearing on whether they sign up for a credit card offer or not. Right? That's our main goal here. We want to see again, is somebody's age tied to whether or not they sign up for a credit card. We have available with us a couple of different metrics. A couple of bits of information to review. We're going to break it up into two parts, prediction and inference. Let's begin with the prediction part of the piece. Our first step would be to figure out, is our model predicting credit card, signing probability using age, is that better than, a random guess? Then we'll examine how good the model is and how accurate the model is. This is all for prediction. Flipping back to our output window, let's take a look at the SPSS output. The first window here shows us the number of observations being 1,000. We can see the two values of our outcome variable are 0 and 1, where 0 refers to no, 1 refers to yes. Now, in the Logit output in SPSS, there are typically two blocks, a beginning block or a block 0 and a block 1. There may be other blocks too, but this is sort of like the basic you're going to see. Your beginning block is like your baseline model. The baseline model essentially is a model with no predictors. Again, much like linear regression, in linear regression, our baseline model is one with no predictors as well. In the absence of any predictors in linear regression, you would assume the average is your prediction, and that is your average is your prediction, right? Okay. Hello. Good. How are you? Absolutely, put me in. If you get it even sooner. Yeah, yeah. I am. I want it done so bad. You tell me a time, I'll be there, pretty much. Okay. All right. Thanks so much. Bye. So we're going to evaluate here our block zero is our baseline block. So you can see out here, our beginning block is one where we assume the existence of no other information available to us. In the absence of any other information, the most natural thing to do is to predict using what you have, which in the case of a binary outcome situation is the majority class. Put differently, if you had to predict, who is it going to be a 0 or a 1, you could look at historical data, right? and quickly look at historical data and say, well, typically, ones show up, and therefore we're going to predict one. One way of thinking about this would be to talk about football, for instance. If somebody were asked, well, what do you think the Jets are going to do in the next game they're going to play? Nothing about the Jets' home game, field, road game, or is it, who they're playing? No information whatsoever. Many people would be inclined to say they're going to lose the game because their track record of winning isn't very good. They tend to lose more games of late than win games. And apologies to Jets fans for that example, but hopefully you get the point here. You can use historical data to quickly kind of figure out, what your baseline prediction would be. So your baseline prediction for credit cards or email clicking and so on, in the same vein, would be most people who get an email marketing offer don't click on the link. Most people who get a credit card offer don't sign up for a credit card. In our data set, we have 1,000 data points. We can look at our data and see in our data set, if you went with that majority class prediction saying nobody will sign up for a credit card, well, in our data set, turns out 52.4% people did not accept the credit card offer. So based on that, we would be correct 52.4% of the times. Okay. All right. So that's our baseline value. Now, there's one other number here that's not expressed in the beginning block, but just to realize that it's been computed somewhere in the background, which is the -2 log likelihood for a model without any predictors in it. It's sort of like it's kind of like an error metric for the overall model. Okay. So in the back of your mind right now should be, we have computed the baseline accuracy. We don't have any variables in the equation. And we have something called a -2 log likelihood that's been computed for the baseline block. Okay. So let's go on to the question of how much better is our model than no model at all? Well, we can do this the following ways. So our model is compared to a baseline model. So the -2 log likelihood for our model in block 1, that is a model with age in it, is 1356.073. You may recall I said in block 0, a -2 log likelihood was computed. It was not stated, but it was computed. The difference between the block 0 and block 1 -2 log likelihoods is your model chi-squared. That model chi-squared reflects how good is your, or how much better is your model than the baseline. Now, we really want to see that our model is better than our baseline, and that's borne out by the p-value for the model chi-squared. So long as that p-value is less than 0.05, we would feel fairly confident that it is, our model is better than the baseline model. The second thing we'll look at here is, now that we know that our model is better than the baseline model, we'll look at our strength of model sort of measures. There are two of them which are used in logistic regression. These are also known as pseudo R-squares. One of them is Cox-Snell R-squared. The other one's called the Nagle-Clerk R-squared. These are two metrics that give us some sense of, again, how good is a model, or goodness of the model. Both these metrics indicate or tell us that the numbers are, it's a weak model because these are both under 0.1. The last element of evidence we'll look at to assess prediction quality is our classification table. Our classification table is telling us that we have, we make predictions, and based on predictions, 52.4% of the people were correctly classified. That's our sort of a prediction accuracy. To get more intuition about what this is, let me just let me go into run a little bit of different analysis, and then we'll get more intuition on where these numbers came from. So I'm going to go back into regression, binary logistic, and this time I'll say save and check the box for probabilities, unstandardized, and group membership. And what this will do is it will give us the same output as before, but our data view will look a little different. If you recall, I pointed out earlier that we get an equation in logistic regression, just like in linear regression. And if you were to plug in the values and you were to do some sort of mathematical gymnastics there, you'd get a predicted probability for any given person or observation. So here we have, in that sense, some predicted probabilities. For the first person, we have a predicted probability of 0.43176 of accepting the credit card offer. Now, second one, 0.43659, 0.44143, and so on and so forth. Now, we need to have some mechanism for translating these probabilities into a binary outcome. By default, we use a 0.5 cutoff, which is why all these 0.4 numbers are all translated to no's. Anything that's 0.5 or higher gets translated to a yes. Now, what's more important here is we really want to focus here on the fact that ultimately we have here what really happened and what we predicted. You can think about 4 possibilities out here. You predicted somebody, would not sign up for a credit card, and they did, right? Or sorry, they didn't. So you can have 4 options: no, no, yes, no, no, yes, and yes, yes. I can't find examples of all of them here, but you get the idea, I'm sure. So anytime you make a prediction that is what you expected, you're made a good prediction, right? So if your offer and PGR1 are the same, you're spot on your prediction. So if you put together all these numbers, you count how many times you got it right, how many times you got it wrong, you'll arrive at a classification table that looks like this. In this classification table, you can see there were 318 instances when we predicted somebody would not sign up for a credit card, and they didn't. 206 when we predicted they would sign up for a credit card offer, and they did. These were the cases when people didn't conform to our expectations. So our percentage accuracy is 52.4%. Let's move on to the last bit of our analysis here. This is the inference part of the story. The inference part refers to figuring out does age, before we do that, let me highlight the fact that our accuracy here is 52.4%. What does that mean? Well, it means we didn't do much better than our baseline. In fact, it's the same number. This should be troubling. So statistically speaking, our model is significant. R squared is showing us a weak model. However, in terms of practical significance, our predictions are the same as having no model at all. That should be a little deflating. Let's go on and look at our individual coefficient here to do some inference work. Now, if you look at the coefficient for age, it tells you that age has a p-value that is below 0.05, indicating age is a significant predictor of whether somebody signs up for a card or not. Now comes the tricky part. Interpreting the sensitivity of the outcome variable to age is the tricky part. To do so, remember, we have to change units. Our outcome variable is in log units. We need to kind of convert. I'm sorry, our right side, left side of the outcome variable we transform by doing natural log of p divided by 1 minus p. So we need to undo that. In other words, our data is in log units. We need to change that. To make that change, what we typically do is do some mathematical gymnastics out here. And so one way to undo a natural log is to, let's say we have natural log of 10. If you do e raised to this number, you negate that log function. In the same sense, what we're going to do here is we will exponentiate our age unstandardized regression coefficient. And that will give us a number of 1.02. This is what we're going to use to interpret age. So what we have then is we're going to look at this number and use this number to interpret the effects of age. And the way to think about it is this 1.02 is compared to a baseline value of 1. So when age goes up by 1 year, the probability of somebody signing up for a credit card changes by 1.02 minus 1, or 1.02 minus 1 times 100%. Put differently, when somebody's age goes up by 1 year, their chance of signing up for a credit card goes up by 2%. This is based on that formula I shared a few minutes ago from the slide, which looked like, this. Okay. E raised to whatever is the regression coefficient minus 1 times 100 allows you to interpret that regression coefficient. So I'm going to come back in the next video. I'm going to talk to you more about how we can use more variables here to improve our prediction quality. Specifically, we use age, income, and home value to predict somebody's likelihood of signing up for a credit card offer.